This video is going to focus on mixtures that contain multiple gases and how we can use the composition of that mixture to determine the total pressure of it, or we could use the total pressure and the information about components of the mixture to determine the pressure or quantity of one of the components, also known as Dalton's law of partial pressures. And we're going to look at the kinetic energy and velocity that we can determine of gases and what factors influence those two. Dalton's law is that the total pressure is equal to the sum of the individual gases' partial pressures. And again, you can get any of those gases' partial pressures if you know how much of the gas you have, its quantity in moles, times the gas law constant in temperature in Kelvin, divided by the volume in liters. The mole fraction is going to determine the relative amount that we have of that gas mixture that's composed of individual gases by taking the pressure of one individual gas, its partial pressure, and dividing it by the total pressure. As we did again in our ideal gas law lab, we collected our gas by water displacement, and water too has a pressure. So if you wanted to find the pressure of that gas, you would need to subtract from the atmospheric pressure, also called your total pressure, the vapor pressure of water. So here we're given a gram of hydrogen and a gram of helium, and it's in a 1 liter flask at 27 degrees Celsius. We're asked to determine the partial pressure of each of the gases and then the total pressure. So we have an amount, we have a volume, we have a temperature, and so when we have those three and we want to find pressure, typically we're going to use ideal gas law, which means we're going to need to convert those grams into moles and the temperatures into Kelvin. So if we take a look at hydrogen first, we would need to convert that 1 grams divided by the molar mass of 2.02 to get our 0.495 moles of hydrogen. There's our constant, there's our temperature in Kelvin, and there's our volume. And when we do those calculations through and we cancel out our units, we see that we have 12 atmospheres of hydrogen gas. And then if we wanted to do the same thing for helium, we would divide the 1 gram by the molar mass of 4, and that would give me 0.25 moles. Everything else will be the same. And when I go through and do that calculation, I get a little less than 12, or sorry, a little more than 12. I get 6.2 atmospheres is the pressure of helium. So to get the total pressure, I need to sum those two together. Each of those combined together will give me my total pressure, which would be 18 atmospheres. If you need to pause, I would do so now. And again, this is from our last video. This is one of those gas laws that allows us to employ both the ideal gas law to use our quantity, and then we can use Dalton's law to solve for an individual pressure. And if we were wanting to relate it to a chemical reaction, we could use those mole quantities to do stoichiometry. So helium gas is collected over water at 25 degrees Celsius and a pressure of 1 atmosphere. What is the total volume of gas that you had to collect to get 0.586 grams of helium? And we are told at 25 degrees Celsius the vapor pressure of water is 23.8 torr. So we need to figure out, first of all, what is the pressure of our helium sample. We know the total pressure, and we know water's vapor pressure. And so we're going to take the difference between those once we get them into consistent units to get the pressure of the helium gas. It makes sense to turn the torr pressure for water into atmospheres, since we know we want atmospheres to use our ideal gas law equation with. So, of course I did it the other way. Yay. Sorry guys. Subtract 23.8 torr from both sides and you get 736 torr. You would need to convert that now into atmospheres before you could solve for the volume, because in order to find the volume that we would need to have at that particular temperature, at this pressure, and for this amount, we're going to use our ideal gas law. So we're going to convert those 0.586 grams of helium into moles by dividing by 4. We're going to use our constant. We converted our 736 torr into atmospheres by dividing by 760. and then we multiply by our temperature in Kelvin of 298. When our units cancel out, we're left with the volume in liters, and that would be 3.7. If you need to pause, please do so now. So the whole idea behind kinetic molecular theory, we talked about this a lot in first year chem, is that there are characteristics that should be consistent regardless of the gas you have, as long as it's an ideal gas. And that is that they are going to take up all space available to them, that they're in constant motion and that they have elastic collisions, that they do not draw towards one another, nor do they repel each other. And as these last two, they're going to play a role in the next part of the video, which is kinetic energy. And that kinetic energy is directly proportional to your Kelvin temperature. It does not matter what gas you have at a specific temperature, the energy of that gas should be constant, and that's because of the size of the gas molecules not taking up or being assumed to be negligible, that they take up very little space individually. So the relationship between kinetic energy and temperature is that 1.5 or 3/2 times the constant in joules, since we were dealing with energy, times the Kelvin temperature will determine for us how much energy is available in motion for these gas molecules. Keeping in mind that the Kelvin temperature is just basically reflecting the random amount of motions that's occurring with the molecules, and obviously if you are at a higher temperature, you're going to see more movement with those gaseous molecules. I said we were also going to touch on velocity, and velocity is your speed, but that is related to your size, because the bigger you are, the little bit slower you move. So to get the root mean squared velocity, we are going to take the square root. We're basically if you know that kinetic energy is 1/2 the mass times velocity squared, we're basically solving for the velocity of that equation in terms of kinetic energy. So if we wanted to solve 3/2 RT, which was our kinetic energy value, was equal to 1/2 mv squared. If we went through and do the math and then took the square root, we would get that 3 times the constant in joules times the temperature Kelvin divided by the molar mass of your gas, but we need to convert it to kilojoules, because joules is in kilojoules, and so that we have consistent units will help us find the velocity in meters per second. So in this particular example, I'm just asking you to calculate the kinetic energy of nitrogen. Again, 3/2 times the constant times temperature. So you don't even have to be told what gas you're working with. All you have to know is the temperature your gas is being collected at. And so we have our constant, we have our temperature, the kelvins cancel out, and we're left with a kinetic energy value, 3 sig figs of 4,030 joules per mole. If you need to pause, please do so now. To get the root mean squared velocity, yes, I'm at school and I'm still getting emails. I'm not the only one here. To calculate the root mean squared velocity, we're going to use the equation that I showed you before the previous example. We do need to know what sample we have or what the composition is of our gas to solve for this, since the gases travel at different speeds depending on their mass. So we know our constant and our temperature, 323 Kelvin. The molar mass of oxygen is 32 grams. So if I divide that by 1,000 to go from grams to kilograms, I will get that's 0.03200. Again, the joules and the kilograms will cancel out, leaving me with meters squared per second squared. The kelvins also cancel out, and that gives me a root mean squared velocity of 502 meters per second. So something to consider, would helium gas travel at a higher or a lower velocity than oxygen? And what about Cl2? Would it travel at a higher or a slower velocity than oxygen at the specific temperature? Okay, that's the end of this video. Now we have one last video to go for chapter 11. Alright, all sorry I did an oopsie. We've got one last one to go. I thought we were done. Here we've got 1 liter gaseous samples of 4 gases, hydrogen, xenon, chlorine, and oxygen. We're told they're all at standard temperature and pressure, so they're all at 0 degrees Celsius. And we're asked how could we separate these out so that, or how could separate samples of each of these gases have the same average velocity. So if they have different masses, in theory, they can't travel at the same speed at a given temperature. But we're asked how could we make them travel at the same speed? And that would be that we would have to adjust the temperature, since those are the only two factors in this equation that we can manipulate. We've got our constant and we've got the 3. So if we have a smaller gas, then we would need a lower temperature so that that ratio would be closer to the others. And we would need higher temperatures for our heavier gases, so they would be moving relatively the same rate as the smaller gases at lower temperatures. You do not have to write everything down that I have here, but just something to keep in mind is that if you want gases to travel at consistent speeds and they have different masses, the temperature is going to have to be adjusted to account for that ratio of temperature to mass. That does end this video for sure. And so our last video is going to take a look at diffusion and effusion and how we can determine pressures and volumes of real gases, ones that have not quite met that 1 atmosphere threshold. And you've seen a few of those so far.